In this example, or series of examples, we're going to do left and right hand approximations. So the way you do this is, given some interval and the number of rectangles, in this case we're going to pick evenly spaced subintervals. So we're going to slice it, in this particular case, into 4 evenly spaced subintervals. Over here, 4 evenly spaced subintervals. And we're going to evaluate the function at the left endpoint, we're going to evaluate the function at the right endpoint, and we're going to see how the sum of those rectangles is different, or whether it is different, depending on which method we use. Now the first one is f of x equals 2x plus 7. And you should be able to visualize that. That's a line with a slope of 2. So you might think that the left rectangle is going to underestimate it. The right rectangle is going to overestimate it. So we should expect that the right-hand sum is larger. But let's do the evaluation and see if we're correct. So so if we're splitting this into 4 rectangles, we have to split this into 4 evenly spaced subintervals. Well, the width is 2. So if I divide that by 4, that means that each subinterval has width of 1/2, giving us an interval length of, or interval of 0, 1/2, 1/2, 1, 1, 3/2, 3/2, 2. Alright, now in this particular case, we're going to use the left endpoint. So we're always going to do 0, 1/2, 1, 3/2. And now we evaluate the function. At 0, that's 7. When x is 1/2, that's 8. When x is 1, that's 9. When x is 3/2, that's 10. Now again, the width of this interval is 1/2. So this becomes 7/2, 4, 9/2, 5. Again, that's 10 times 1/2 is 5. 9 times 1/2 is 9/2. So each time we're multiplying by that width of 1/2. So if we add that together, we get 16/8. So it's 8, 12, 17. So our left sum is 17. Next, we're going to evaluate the right-hand sum. So the right endpoint is 1/2, 1, 3/2, and 2. So if we evaluate the function at 1/2, well, we've already done that, it's 8. At 1, we've already done that, it's 9. At 3/2, we've already done that, it's 10. And at 2, we get 11. Now we need to multiply this by 1/2, so that's going to be 4, 9/2, 5, 11/2. So when we add that up, that's going to be 17/2, 27/2, 20. No, that can't be right. So this is going to be 20/2, which is 10, plus 9 is 19. It should have been 17, 27, 38/2. That's what it was, instead of 28/2. So the right sum is indeed larger than the left sum. Now over here, we're going to do a very similar process. Notice that the width, again, is 2, so that if the total width is 2 and we split it into 4 rectangles, then delta x is 1/2. So we can split this into intervals of length 1/2. So we're going to do 3 and 7/2, 7/2, 4, 4, 9/2, 9/2, 5. So we're going to pick our left-hand interval. Now in this case, I didn't point this out, but this g of x function, this is a parabola. This is a parabola that eventually opens up, but let's see, the minimum of this parabola is, 4x minus 1, so it's at x equals 1/4. That sounds about right. X equals 1/4 would be the minimum of the parabola. So if the minimum happens at x equals 1/4, then everything after 1/4, it is increasing. So if I take the first derivative, I get 4x minus 1. If I plug in 3, that's 12. If I plug in 5, it's, 19. Or yeah, it was 11 and 19. My goodness, I'm doing this on the fly, and it shows. And so what we're going to find is this is actually increasing all the way through. And if we do the second derivative, we're going to find it's concave up in that location. So it's always going to be increasing. That means that our left-hand sum should be our underestimate, and our right-hand sum should be our overestimate. But let's see if that bears out here. So when I take the lower end, that's going to be 3, 7/2, 4, and 9/2. When I take the function value at 3, I get 18 minus 3. 15 minus 1 is 14. Let's see. If I take 7/2 and I plug it in there, I'm going to get 20. If I take 4 and I plug it in there, I'm going to get 27. Did this on a computer to try to make sure I didn't make a lot of mistakes. This is a lot to plug in on the fly. But let's just check it for 4. So I make sure my computer program ran okay. That would be 32 minus 5 is 7. I take it for 9/2, and the value comes out to be 35. Now my computer program, I did do something wrong, so I will have to do this manually, but it shouldn't be too bad. So we multiply by 1/2, that's the width, so we end up with 7, 10, 27/2, 35/2. So that becomes 62/2, which is 31, 41, 48. So my left sum, I get 48. All right. Now over here, take 1 second here. Just 1 second. Should be 14. I just want to make sure. I feel like something's wrong. So I wrote this computer program. The computer program is telling me, it's giving me like half the number that's here, and so it kind of it's freaking me out. I want to make sure I'm doing this right. I want to make sure I have the right answer. But I'm doing this the analytical way, and I'm coming out with 18 is the actual answer here, using a little bit of mental math, and that's between 17 and 18. So that makes me think I'm doing it right. This one's a little harder to figure out on the fly, because you can, let's see, I can do this and it would just be kind of gross. So let's not. All right, so let's take the right-hand approach. In this case, it's going to be 7/2, 4, 9/2, 5. Again, we're just taking the right endpoints here. The function value at the right endpoint, we've already done that. That's 20, 27, 35. And then I have to plug 5 in here. So that's going to be 50 minus 6. So that should be 44. Did I do that right? That is correct based on what I have there. Take this, divide it. If we multiply by 1/2, we get 10, 27/2, 35/2, and 22. So that's 31. When you add that together, 41, 63. And those are the left and the right hand sums for those, and so those are actually very clean, but you may not get clean answers when you perform these types of problems.